Hello, in this lab, we explored the behavior of DC and RC circuits using real circuit components. The purpose of this lab was to predict and measure currents and voltages in a series of DC circuits and examine the charging and discharging behavior of a capacitor in an RC circuit. We used fundamental physics principles like Kirchhoff's loop rule and charge conservation to model the circuits. By the end of the lab, we discovered how resistors and capacitors behave in these circuits and compared our measurements to theoretical predictions. For the DC circuit, we set up a series circuit with two 1.5 voltage batteries, two resistors, and two ammeters. We predicted the currents I1 and I2 using Kirchhoff's loop rule and charge conservation. Initially, the ammeters read 20.3 milliamps. When we reversed one ammeter, it read negative 0.02 amps, indicating the direction of current flow. The voltmeter measured 3.07 volts across the resistor. Interestingly, when we placed an ammeter in parallel with the 100 ohm resistor, the current through the first ammeter increased from 20.3 milliamps to 59.1 milliamps. These results matched our predictions, showing how currents and voltage behave in a series circuit. Next, we investigated an RC circuit using a capacitor, a battery, and two light bulbs with resistances 2 ohms and 5 ohms. For the 2 ohm bulb, the bulb lit up and then dimmed over time as the capacitor charged. It took 9 seconds to charge fully. When the capacitor was disconnected from the battery and connected directly to the bulb, it discharged in 13 seconds, with the bulb starting bright and then dimming. For the 5 ohm bulb, the charging time was slightly shorter at 8.5 seconds, and the discharge time was 10 seconds. This behavior is explained by the exponential decay of voltage across the capacitor, governed by the time constant RC. The 2 ohm bulb had a longer discharge time because its lower resistance allowed more current flow, discharging the capacitor faster. Now let's address the question, what if you charge the capacitor with no resistor in the circuit? In an ideal model, the capacitor would charge instantaneously because there's no resistance to limit the current. However, in real life, the capacitor doesn't charge instantly. When we connected the capacitor directly to the battery and ammeter, it took 9 seconds to charge. This is because real circuits have internal resistance in the wires, battery, and ammeter, which slows down the charging process. In conclusion, we successfully analyzed both DC and RC circuits. In the DC circuits, our measurements matched theoretical predictions, and we observed how adding an ammeter in parallel affected the current. In the DC circuit, we observed the exponential charging and discharging of the capacitor with different time constants for the 2 ohm and 5 ohm